Okay, so now this is the hardest part, is when trying to describe prescription of motion for little bits of things. We got a handle on this acceleration term, mass term, but it's these forces that end up are the hardest part about all of fluids commonly, because you just have to describe so many things and break it up into so many different components of force itself. So yeah, I highly recommend you read the textbook section on this, because every person should digest the meaning of this stuff separately if you're going to go on to do more things. And it's just a good way to understand how differential elements can experience forces. But you always draw, right? You draw the coordinate system. We always draw little bits of fluid. So before I was doing blobs, but for this force stuff, a cube is very helpful because the areas are easy to calculate, and they make them, well, you can make them quantifiable things that have just an arbitrary blob of fluid. But, right, we are then going to just try to describe the forces acting on this, and this sits in some volume of fluid. So let's say this is V, and I'm looking at a small bit of volume. So that's where you have this delta V in your book. You just call it some little tiny bit of fluid. So there's a couple steps I've written in the notes that just kind of describe how all of these derivations and what they're getting at when they're trying to describe these things. So you have to have this is a little bit of Y, this is a little X dimension, right? This is a little bit of Z, so you have these small, tiny cubic dimensions. They don't really matter actually in the end because they're going to limit them to 0. But I like in the book what they do is they consider these very center of this cube. We'll call those actual points sitting inside the cube. So it's internal to this little bit of cube. So that's the center of mass, so let's say, of this entire cube. And then what you want to get at is, for this little bit of fluid, right, there are forces that can act, they are body forces that would be acting on the center of mass. Remember that from physics, that body force acts on the center of mass, an actual point, so that would be something like the gravity force that acts on the center of mass. But then since you've considered a little bit of fluid, there are other ones that are surface forces. And those are the ones that just eat up so much paper when you're trying to write these things out, because you could have these compressive forces on the side of it, and you can also have these shearing forces in 2 different dimensions. So that's one of the hardest part about these, because there's how many sides to a cube are there, and then you have to describe each single one of those sides based on differential things. So the whole point is you go from here and you write out body forces. That's usually the gravity force or other forces, right? Magnetic forces can be a body force, gravity forces, anything from a conservative field can be a body force. That force is acting on the center of mass of your little cube of fluid. Then there's also the surface forces that we have to now define using, right, other fancy differential terms. What they're getting at is what's happening on the actual surface of this cube. Right? And if you just look at one side of the cube, you can see that the summations, right? So if I just look at one face of the cube, right? Here's the center of mass. I could have these compressive forces on the side, and then I also could have these shearing forces. Say something that looks like that. So if you're summing forces in the X direction, you have to consider, right? You have to consider this one, and this one, where these ones are tangential and shearing, and these ones are, let's say, compressive or tensile stresses. So that's where these derivations head. I just wanted to give an overview of where you go with these types of calculations and differential analysis.